So welcome one more week. This time is lecture 7. We are halfway through the course already. Lecture 7 of Introduction to Quantum Optics. So today it's also a very special day because we are going to study finally in a bit more detail the interaction between light and matter. We started already last week very briefly, and I will summarize now. But today we will go full on into how do we describe the interaction between light and matter a bit in general, and then particularizing to a single atom interacting with light. So let me just go back because we will be using today many things of the atomic physics that we were studying last week. Let me just go back and make kind of a small summary of what we saw in there. So let me go here. Okay. So I remind you very quickly that what we saw is that we define in quantum optics matter as basically anything that has a non-uniform structure, energy structure, okay, and couples to the electromagnetic field. So basically anything that fits that description, we will call it matter, but we saw it through the specific example of atoms, and in particular, these simple atoms that have a single valence electron. So they are kind of like hydrogen. So in principle, we saw that this is, or it looks like a very difficult problem because we have an electromagnetic field with many modes interacting with a structure, an energy structure that has no order. It's very non-uniform. But what we saw as well is that when we consider one particular frequency of light interacting with the many multi-level structure, at the end of the day, because the energy is exchanged in packets of h bar omega, and then let's say electrons can make transitions between orbits, between atomic orbits, just absorbing that h bar omega, energy conservation tells you that only the levels that are close to resonance, so the transition of these levels is close to resonance with h bar omega, then they will matter. Anything else will not matter. And this is what we call the two-level approximation, meaning that when we take matter and we radiate it with light at some frequency omega, we can forget about all levels but two, one that we call ground state and another one that we call excited state, okay, whose energy difference matches more or less the frequency or the energy of the quanta of the monochromatic light that we are using. And therefore, the Hamiltonian of the atom, which in general is, it has a spectrum that looks as complicated as this, at the end of the day, it's simplified to something as simple as just the projector of the ground state and the projector of the excited state and times the energy. So then once we have mapped our matter to a two-level system, we can start using all the mathematics of two-level systems or spin one-half systems. In particular, we define the Pauli operators, and then we saw that the Hamiltonian, we can rewrite it, just making a shift of energy to the middle, to the center of the transition, okay, between the ground and the excited state. We can make the Hamiltonian look like a sigma set, okay? And we call epsilon to the transition frequency. So the energy is h bar epsilon. Okay, then the other important thing that we saw is that the state of a two-level system, so the state of matter within this two-level approximation, can always be written, any mixed state can always be written as half of the identity plus a linear combination of the Pauli operators with some coefficients b that define a vector that we call it Bloch vector. And what it satisfies is that the absolute value of the vector, so the modulus of the vector, has to be smaller or equal to 1. So any state like this, okay, any state like this, it's accessible or available a matter state within the two-level approximation. And just because we will use them today, just I remind you that we define something called the population, which is a special observable that tells you how much of the atom is in the excited state or in the ground state. Okay, so just remember this definition that will be important. It's just the probability of the atom to be in the excited state or in the ground state. So we will be using this today. Okay, we also saw that this coefficients B, this Bloch vector, has a very nice interpretation, in particular as the expectation values of the Pauli operators, okay? This means that we can make a representation of matter states or atomic states in a space, in a three-dimensional space, in which we write down on each axis, we write down the expectation value of one of the Pauli operators. And then one point in this space gives you one of the vectors B that define a state. Because the restriction that the absolute value of B has to be smaller than 1, then out of this space, the only part that it's important is whatever is inside a sphere of radius 1, okay? And all that defines what we call a Bloch space, okay? Bloch space. That's why we call this Bloch vector. And then in this Bloch space, what we saw is that when we are at the origin, so when B is equal 0, okay, then we have what we call already the maximally mixed state, okay? So the state in which we have absolutely no information about the state of the system. On the other hand, when B is equal 1, okay, so the absolute value of B is equal 1, this defines a sphere in this space that we call the Bloch sphere, and it's a very special manifold of this space because the states that lie in that manifold, in this Bloch sphere, are pure, okay? And actually, if we write the B vector in spherical coordinates, okay, so which means that we have two angles. One angle is the polar angle, and the other angle in here is the azimuth angle. Then the pure state can be written in this funny way, in which the polar angle simply gives you the relative phase between the ground and the excited state, okay? And the azimuth angle just gives you the weight of the ground and the excited state, okay? So I think I didn't mention it, I forgot, but I hope it's clear that, of course, because of this, when we are in the North Pole, okay, when we are in the North Pole of the Bloch sphere, then we are in the excited state. So this means theta equals 0, and theta equals 0 removes the ground state part and leaves you only the excited state part. And then if we go all the way down to the south, okay, the South Pole, that's the ground state, okay? And on the other hand, the eigenstates of sigma y or sigma z, they lie on the equator, okay? So on this theta equal pi over 2. So this is just so you have an intuition about where you are in Bloch space or how is the state depending on where you are in Bloch space. Okay, then we finished the lecture talking about dynamics, in particular unsupervised unitary evolution of these two-level systems. And what we saw initially is that any Hamiltonian, the most general Hamiltonian of a two-level system, we can write it as a linear combination of Pauli operators, okay? And if we let the coefficients in front of these Pauli operators to be any time-dependent function, okay, that defines a vector, then this is the absolutely most general Hamiltonian that you can think of, okay? Just choosing different functions of alpha, alpha of t, then you get different types of dynamics, and that's the most general we can do. Then what we saw is that the Schrödinger equation or the Heisenberg equation, so quantum dynamics, it's equivalent to an evolution equation for the Bloch vector, okay? And in particular, it's an evolution equation that is especially simple because it's a linear equation, just like the Schrödinger equation is linear and so on. So the equation for the Bloch vector is also a linear equation, only with 3 variables, because the Bloch vector has 3 variables. And therefore, this can always be solved in the worst case numerically. Okay, so it's very, very easy to solve, at least numerically, these 3 equations, these 3 linear coupled equations. But then we went on and we started studying, well, before maybe very quickly, I remind you also that unitary evolution or unsupervised evolution happens in a subspace in which the Bloch vector, the absolute value of the Bloch vector, remains fixed, okay? So this means that if you start in one specific value of B, then you will move only along a sphere that has the same radius as you started from. And that's kind of obvious, or we saw that it was obvious if you think in terms of mixed states and entropy, because the entropy depends only on this, okay? Because the eigenvalues of the density operator depend only on the absolute value of B, and therefore the entropy, so saying that this is fixed means that the entropy is fixed, and we know that unitary transformations do not change the entropy. Therefore, unitary evolution and Hamiltonian evolution needs to happen along a sphere of fixed entropy, okay? And then finally, we also saw that we can rewrite, or we can redefine the Bloch vector in terms not of the X and Y components, but define a complex component out of them, okay, that we simply call B. And this gives you the complex Bloch equations, which are the previous equations in terms of a complex variable and a real variable B set. So then we have just these simple looking equations. That is the form that we are using to essentially solve the problem. Okay, so then given these equations, we started, this is more or less where we were, we started checking interesting types of evolution. And in particular, the first one that we checked was evolution given by do nothing on the atom. So what does it mean, do nothing on the atom? Just let the atom evolve according to its Hamiltonian sigma set, okay? So in the language of the form of the Hamiltonian, in which we write it as a linear combination of Pauli operators, this would mean that alpha is just equal to 0, 0, epsilon, okay? And this means that the evolution equation, the complex Bloch equations, are given by this form in here, that is very simple because it tells us that B set doesn't change in time. So if we start with one population in the excited state and one population in the ground state, we keep that throughout the evolution. And B of t, so this complex B, evolves according to just phase linear with time, okay? So when we write this in the Bloch space, so in the original Bx, By, and Bz variables, then what we get is that this is a rotation in the parallel to the XY plane, or if you want, is a rotation around the Z axis. And this is essentially the plot that I showed. I changed it a little bit from what I showed before. What I have put in here is this trail that tells you in which direction you are rotating, okay? So this is rotating in this direction, okay? And essentially this is what you see. If you start at any point in this trajectory, what you will see is that the Bloch vector with time, it just moves around this circle, okay, harmonically. And this is what we call spin precession, okay? So we have a precession of the spin along or around the Z direction. So this is free evolution, and it's just something as simple as this. Then what I want to do today, what we started seeing a bit yesterday, so let me go to the new part of the class, is what we call the evolution given by the semi-classical Rabi Hamiltonian. So what is the Rabi Hamiltonian? So it's a Hamiltonian that simply has the free evolution of the atom plus evolution along sigma x, okay? In particular, with a harmonic coefficient that goes with a well-defined frequency omega, so it's a time-dependent periodic function of some frequency omega. And what I already showed you, or I tried to convince you about, and we will see today in more detail when we study light-matter interaction in more detail, is that actually this situation describes the interaction of matter, or our two-level system, with classical light, classical monochromatic light of frequency omega, okay? So for now, you just have to believe me that this is the case, but we will see it today or maybe in the next lecture, but in the next chapter, we will see it in detail. So then, because this is the interaction between matter with classical light or with light at some frequency omega, we already have an expectation, which is that if the frequency is far from the atomic transition, from the matter transition, then we expect that nothing happens. That's how we started the chapter and how we started with the two-level approximation. We assume that our mathematics will give us that when omega is larger or it's different, much more different than epsilon, then nothing happens. And what we will see today is that this is exactly what happens. And actually, we will understand what it means to be larger or too large or too small compared to epsilon. Because right now I am just saying if it's much larger, but what does that mean? How do we quantify when it's too large or when the difference is too large? So we will see that today. And then the other assumption that we will make to make things easier, and also because it's what usually happens in optics, is that this amplitude of the modulation omega, okay, so the strength of that part of the Hamiltonian, okay, it's much smaller than the frequency of light, which, as we will see, is on the same order of the atomic transition. So essentially, what I am saying is that the interaction of light with matter is just a perturbation onto, okay, the atomic spectrum. And this is kind of easy to understand because when it's not a perturbation, then you cannot really distinguish very well between the initial atomic structure that you had and your light field, because if everything is mixed up and the energy levels are changed a lot, okay, then you don't really have just matter interacting with light. You have a new combined system that will be very complicated. And maybe we will see something about that because that's a very interesting regime, but it's definitely not the regime that we are more interested in. So, so essentially, this is the assumption that we will make, okay, that omega, so the strength of the interaction is much smaller than the frequency. This is very well satisfied in optics, as I was saying, because we will see that this strength of the interaction depends essentially on the strength of the electric field, okay? And the electric fields that would be required to reach frequencies on the order of 10 to 15 hertz, which is the optical frequencies, are incredibly large. They are just too large. You would break the sample before you actually are capable of studying the interaction between light and matter. So there are other systems which are not optical systems, but microwave systems and so on, where it's easier to reach this regime in which omega is similar to the frequency of light, but we will not study them right now, at least. Okay, so then let's start the new part of the lecture by analyzing the dynamics given by this Hamiltonian, which I hope I have convinced you that it's a very important Hamiltonian in quantum optics. So the first thing that we have to do is write down the Bloch equations. So how do the Bloch equations look in this case? So you can just check from the previous slides that we will have something like this. So first, the part given by the free term, okay? And that gives us just this. But then we have to add the part of the time-dependent part of the Hamiltonian, so the light matter interaction part, and we will get something like this: cosine of omega t, b set, and then in here, 2I omega cosine of omega t as well, and then b minus b star. So we see that the effect of this term, first of all, is coupling the evolution of b to b set and the evolution of b set to b, okay? Okay, so first of all, let's talk about expectations. So as I was saying, essentially we expect this to be a perturbation, okay? And therefore we expect b to still evolve at, or let's say it's the evolution of b to be dominated by essentially oscillations at the frequency of the atom, okay? So then we will have some fast oscillations of b at atomic or optical frequencies, and then we will have some modification of that because of these terms, okay? Then it's very convenient to do something. It's very convenient to, so let me write it down here. It's very convenient to define a slowly varying variable in this way. So we define another b, okay, which I call b tilde, because it will be the original b, so b of t, but we just remove from it evolution at optical frequencies, okay? So it's very simple to understand what this is, because this b, we expect that it is oscillating at optical frequencies, or if you want at frequencies epsilon, okay? And then when you multiply it by a phase factor, which has the opposite type of phase, so the plus instead of the minus, then what you are doing is discounting the evolution at frequency omega, okay? So omega is close to epsilon, and therefore when omega is equal to epsilon, you are discounting the full free evolution. And then this thing here can be seen as a slowly varying amplitude or variable. Okay, so it's just the original B, but oscillating much slower. And this is very convenient for many reasons, both for numerics and also for analytics, as we are going to see right now. But it's just a change of variable, so we haven't done anything special by just changing the variable. So then in terms of this new variable, these equations look like this. So the derivative of this new variable, it's equal to something like this, plus, and then we have here I omega halves, and then 1 plus E 2I omega t and B set. Okay, and then similar for B set, we can write it as I omega, and then 1 plus E 2I omega t B tilde minus the complex conjugate. Okay, so this means complex conjugate. So what's interesting here is that because of this change of variables, now we have been able to write down the equations in a way in which essentially we have separated the fast scales of the equation and the slow scales of the equation. And this we will see now in detail. In particular, now the fast scales are all contained into these time-dependent factors, which even if the equations look simple, they still make it very hard to solve. So in particular, the time dependence of this equation makes it hard to solve. And in particular, hard to find analytic solutions. So actually, these might have analytic solutions, and I work on methods actually that are able of dealing with this analytically. But of course, these are very advanced things that are not so interesting for an introductory course. And here, what we will do is we will see, or we are going to see right now, that actually these fast terms, these rapidly oscillating terms, we can get rid of them. And this brings me to essentially the most important approximation together with the two-level system approximation that you will see in quantum optics, and this appears everywhere in quantum optics, which is called the rotating wave approximation. Okay, so this is a very general approximation that works for many, many types of systems. And here we will see it for this one, but we will be using it throughout the course for many other types of interactions, as you will see. And this rotating wave approximation, essentially in loose terms, so the raw version of this is just neglect rapidly oscillating terms. Okay, so now I am going to justify why we can do this, but essentially this is something you have to remember for life. Whenever you have an equation that has fast scales and slow scales, especially periodic fast scales and slow scales, then you can take the fast scales and basically neglect them. And you might have seen this approximation actually in other contexts, even in classical physics, but it's something that it's especially useful in our quantum optics context. Then let me just give you some intuitive justification. So intuitive justification. And this we do very easily by simply doing a time average of the equations that we have over an optical period. Okay, so which means that we take the equations at some time t, and then we make an average from time t minus pi over omega to t plus pi over omega. Okay, we are going to do an average of the equations. So averaging means that we just take the integration from t minus pi over omega to t plus pi over omega in the time variable, which I will call t prime, and divided by the period, which is omega divided 2 pi. So we do this operation, so this averaging for these equations here, okay? So when we do that, what we will get are terms in which we essentially, because these equations are linear, okay, what we will get is that averaging the equation, it's essentially the same as averaging the B or averaging the B set, okay? Or the B or B set multiplied by these factors, oscillating factors. So essentially what I am saying is that we get two types of averages. One is this, okay? And the other one is, so the same type of averaging over optical periods. And then here, instead of just B, we will have B times 2I omega t prime, okay? These are the two types of terms that appear. Of course, the same with B set and the same with B set. So these are the four types of terms that appear. And now what we will show is the following. So I give you here the main argument. The main argument is that, so we have seen that B tilde and B set, so the time derivative of that, it goes as omega minus epsilon or as omega. So as you have here, this is the expectation, okay? The expectation is that B, so B dot and B set dot go as omega minus epsilon or omega, okay? And then we expect this term not to do too much damage. And I give you the reason why here, because these two frequency scales, so omega minus epsilon and capital omega, these are way smaller than the frequency omega. And then we can say that B tilde and B set behave essentially as constant. Okay, so essentially this is an implication of this. So constant over an optical cycle. Okay, so if you want, I tell you things in a more physical way. We have seen that this variable here, we expect it to be slowly varying, okay? Slowly varying with respect to optical frequencies, to epsilon. And then this means that within an interval that is given essentially by an optical period, so by pi, 2 pi over omega, this variable here will not change, okay? Will be essentially the same value at all times between t minus pi over omega and t plus pi over omega. So then this automatically means that we can put this variable outside of the integral. In particular, we can take it at time t in the center of the interval, in the center of the cycle. And all that is left is the integral part, but the integral, this integral is exactly equal to this factor here. So then we get just 1, okay? On the other hand, in this case, we get something very different in this case in here, because if now I use that this B is essentially fixed, so it doesn't change in time within this period of time, okay? Then what I get, it's that I can put it out as well, B of t, but now I get the integral, not the trivial integral of 1, but the integral of this exponential factor, of this harmonic term. And of course, the periodicity of this factor is exactly half of the cycle that we are checking. So in other words, we are doing 2 cycles of this harmonic function, and therefore this integration is equal to 0. Okay? So this is a very intuitive justification of why we can actually neglect these kind of terms. So these kind of terms, these rapidly oscillating terms, we can neglect them in the equation because if B is slowly varying, okay, B and B set are slowly varying variables, then essentially the contribution of these terms will cancel to 0, okay? And this is something that I am just justifying intuitively here, but we will actually see the rigorous proof. Okay, based on perturbation theory. And this you will see by yourself in an exercise. So the exercise of this chapter will be precisely about doing perturbation theory of this equation, okay, treating omega as a perturbation, okay, so treating this Hamiltonian as a perturbation over the bare atomic Hamiltonian. So in any case, I hope that at least this convinces you that this rotating wave approximation will work very well in optics because this slowly varying variable doesn't really change much within optical frequencies. And this is something that we need to be able to prove after solving everything. So we have to check for self-consistency. We have to show that these variables B and B set evolve in some way, but we have to make sure that the way that we find that they evolve is actually slow compared to the optical frequencies omega, okay? So this is self-consistency, and it's something that you always have to check whenever you do approximations in physics. So this will help you throughout your career. Whenever you do an approximation, that's okay. You can do as many approximations as you want, but always check that the assumptions that you made the approximations based on, then they are consistent with the solutions that you are finding, okay? This is something very, very important. Okay, so then let's rewrite the equations now that we know that we can remove those terms, and in particular, let me define a parameter that it's the optical frequency minus the atomic frequency, and this is a very important parameter that we call detuning. Okay, so this is the detuning between the light that you are sending to the material and the transition that you want to excite in the material. And this, with this definition, then the Bloch equations turn into these equations here. Is a tilde. Okay, so now these equations are time independent and finally can be solved analytically. So these equations, we can solve them analytically in a relatively simple way. I will not do the solution here, but you have it in the notes in a lot of detail. And I encourage you to go and check it out because the way I solve it based on the eigensystem of the linear matrix that defines a linear problem, it's a method that is completely general and you can use for any linear system. And actually we use it all the time in physics for any type of problem. So for every problem I work with, I always use that method to solve the equations, either numerically or analytically, okay? And in particular, in this case, everything is analytic and it gives the following solution. So let me just present you the analytic solution. And the analytic solution can be written in terms of just two parameters. So again, we have also two parameters in this equation. No? We have delta and omega. So I will define a normalized detuning, which is the detuning divided by the strength of the interaction or the perturbative part of the Hamiltonian. Okay, so this is just a redefinition of the detuning or a normalization of the detuning. And then we define also something that we will call the Rabi frequency. That is delta squared plus omega squared, the square root of that, okay? So these two parameters are the parameters that define the solution. And the solution, as I said, is very easy to find. It's the only thing is that it's a bit big to write, okay? So I don't want to waste too much time writing it because it would take me maybe even a few minutes. So what I will do is I will just take it from what I already wrote before coming to class, and you have the solution here. So don't worry about copying it, okay? So you don't need to copy it, you have it in the notes. So just pay attention to it for the time being. This is the solution. It looks very big, but it's a very simple solution. And I want you to focus only on two things. So first of all, both B set, so the populations, the excited state population and the ground state population, and this B variable, both of them oscillate with cosines and sines that have this frequency omega r, okay? So this oscillation, in particular the oscillation of the populations between the excited and the ground state, that we call Rabi oscillations. Okay, and that's why this parameter here is called Rabi frequency. Okay, so this is something that we will see now in a lot more detail, these Rabi oscillations, but these are a very, very important concept in many fields, in nuclear magnetic resonance, for example, but in quantum optics as well. And then the other thing is that we are going to study specific limits of this equation. And in particular, the first limit I want to discuss is this limit that I show you here, in which the detuning is very large. Okay, so what happens when we detune the light that we are using, so omega, very far away from the atomic resonance, from epsilon. So this essentially means delta much larger than 1. And just take a look in here. So what happens with this solution, I marked it in blue, is that the denominator of the solutions go as delta square, okay? And then if you check the numerator, in the numerator you have b's, but the b's are bounded by 1. That's what we know from physical states of the two-level system. And everything else is also order 1 or order delta, okay? So you can see this term here, for example, that is delta. Then when you divide delta by delta square, you get 0 in the limit of delta going to very large. Then the only term that survives is the delta square term, in which you have that BC, it's equal to BC of 0, okay? So let me just write down here the solution that BC of t, it's equal to BC of 0. On the other hand, for the B variable, here we have only one term that goes with delta square, okay, which is this term in here. And everything else, sorry, and this term in here as well. So we have here a term that goes as delta square square root, and then a delta here. So we get these two terms, and one has a cosine, the other one has an I sign. So when we put them together, what we get, it's essentially that B tilde, it's equal to E to the I delta t, B of 0. Okay, so this is what the solution says. Of course, let me also remind you that the frequency here is omega r, not delta. But of course, when you take the limit in which delta is much, much larger than omega, then you can forget about this omega term, and omega r becomes delta, okay? So essentially, this is the solution in the limit delta much larger than 1. And if we come back to the original variable, not the slowly varying, but the original b, this is equal to b of 0 e to the minus I epsilon t. And what is this? We have just talked about it. This solution is just the free evolution. Or if you want, the evolution of the atom when we do nothing, okay? So we have shown that in the limit in which the detuning between the light that you are sending and the atomic transition is very large, then the interaction is like it doesn't happen. So we have just the evolution given by the free evolution of the atom. And therefore, this is the first justification of the two-level approximation that we have made. Okay, so in particular, I remind you that only transitions that have epsilon approximately equal to omega are important, so matter. Okay, so this is the first rigorous justification of the two-level approximation. So at least in a simple form. Okay, so this is the first limit. Then let me show you a second limit. So this is very, very important. So this limit we have seen is very important because it justifies a two-level approximation. But now there is another limit, which is kind of the opposite limit. So it's the limit in which the detuning it's equal to 0. So what happens when we actually shine light that it's exactly at resonance with the two-level system, with the atomic transition? Then it's very simple in the equations to see that they simplify to a very simple expression that looks like this. So first, we will write the solution in terms of the real components directly. So we have the slowly varying vector. So we will call this P tilde. It's equal to just a rotation, but a rotation at frequencies omega, around the x-axis, not the z-axis like for free evolution. Okay, this is the solution. You can just check that if you go back to the solution that I wrote and you put delta equals 0, you get this simple solution. And then this is equal. So what is this? This is just a, and this is important, a slow compared to optical frequencies, left-handed precession around the x-axis. So you see that you are mixing the components y and c through a rotation at frequencies omega, okay? So this is telling you that free evolution was a fast rotation around the z-axis, okay? That was the evolution just of the atom without doing nothing. And then if we discount that with what we have already done in here, with these slowly varying variables, what is left is just a slow rotation at frequency omega, much smaller than the optical frequencies, but around the x-axis. So let me show you in a figure how this looks. So I think I have it here. So essentially, this is what I'm saying. So again, we have here sigma z, sigma x, sigma y. So this is Bloch space. We start, for example, here, okay? So we start in the excited state in the North Pole. And then what this equation says is that with time, what you will do is you will just move periodically along a circle, okay? Around a circle that moves parallel to the ZY axis. So it's a rotation around the X axis, okay? And in particular, this is what you see for the slowly varying vector. But also let me show you something more, because this is, as I said, for the slowly varying vector. But I want to show you the real trajectory, as you will see it in the lab, when you consider also the rotation around the z-axis, because this is only the rotation around the x-axis that is slow. But when you go back to the original variable b, then what you get is a much funnier trajectory. So let me keep this here for now. You see a much funnier trajectory that looks like this. So it looks pretty cool, no? Like the idea now is that For the slowly varying vector is just going down from Z to Y, let's say. But while it is going down from Z to Y, at the same time, the real vector is moving around the Z-axis, rotating around the Z-axis faster, okay? And therefore, the real trajectory, it's a spiral, okay? You would see this funny spiral in which the block vector just goes down in this spiral way, okay? But it's even funnier because here I am showing only half of the trajectory. I'm showing how you go from the North Pole to the South Pole. But how do you go back? You don't go back through the same spiral, okay? You go back through a different spiral. And let me just show you. So this is just a bit for fun, a bit so you see it, because I was never shown this, and this is actually how it would look in the lab. So it comes back through a spiral, but it's a spiral that is not the same one as before. And therefore, you will see kind of this double spiral trajectory that looks very complicated and very funny, but you see that it comes from something very simple. It's just a slow rotation around the x-axis and a fast rotation around the z-axis, okay? So this is something that is very important for you to get used to visualize trajectories and so on, and in physics in general. This is not for quantum optics. So essentially, this is all I want to show you about this resonant case, okay? The case in which the detuning is equal to the atomic, sorry, the optical frequency is equal to the atomic transition frequency. And you only need to remember, of course, that you have a slow oscillation around the x-axis, but I want you to also see how is the real trajectory in the original variables. So I think we can make a break now. So welcome from the break. So we were analyzing what is the evolution that it's provided by this Hamiltonian, okay, that describes the interaction of our atom with a classical monochromatic beam or classical monochromatic light. And what we have seen is that the solution, so we can find the solution analytically if we make the rotating wave approximation. And then we have analyzed two limits. First, the limit in which the detuning is super large compared to the interaction or the coupling between the atom and light. And then in that case, we recover free evolution, and this justifies the two-level approximation. So perfect, like we expected. And second, the opposite limit in which the detuning is equal to 0. So we are shining light that it's exactly resonant with the transition we are investigating. And then in that case, what we see is Rabi oscillations between, so that are essentially a rotation, so a precession around the x-axis. So this is for completely general states. So this depends only on delta. So when delta is large or delta is equal to 0, this is what we get for any type of state. But now let me discuss one more limit that it's a very interesting limit, which is the limit in which we start from the atom in the ground state. So we start from 0, 0, minus 1, okay? Or if you want psi of 0, it's equal to the ground state, okay? So now we allow the detuning to be anything, whatever, but we start from a very special point, which is the atom in the ground state. This is actually the most, let's say, natural situation in which you have your atom in the ground state very happily, and then you disturb it with some light field, and you see how it evolves, okay? So then essentially, in this case, let me define, well, let me remind you that this parameter small delta was just the normalized detuning. And then in this case, you can see that the solution is very easily written in terms of the x and y components in this way. So let me just write it down so you see exactly. So this is Bx, then we have By, which is the sign. And then finally we have Bc, which is delta square with a minus. So delta square plus the cosine. And 1 plus delta square. So this is the solution in this limit in which you start. So the initial condition is the ground state. And I will show you the trajectories in a second, but it's also important that from this, we find the excited state population. So this is kind of the most important observable in this case, because what you are asking is, okay, I have my atom in the ground state, I shine light. What is the probability that I actually make a transition to the excited state? So that's given by 1 minus cosine of omega RT divided 1 plus delta square. Sorry, there is a factor 2. Okay. So you can check that this is the result, and let's then discuss it. So I show you the plots to discuss it. So first of all, let me show you the trajectory. Okay, so this trajectory here, okay, the slowly varying vector, what it's doing is the following. So we always start from here. We start always from the ground state, from the South Pole. And then we have evolution that follows one of these circles. So these circles here are for different values of the detuning, okay? So for example, we have already seen the case of delta equals 0. In the case of delta equals 0, we saw that what we get is a circle that goes just between the x and y axis, okay? So we go from the ground state all the way up to the excited state, and then back to the ground state, and then back up to the excited state. And we will have oscillations between the ground state and the excited state, okay? So this corresponds to this circle here, okay? Delta equals 0. Now, what is the effect of the detuning? And that's why I'm showing this figure. So as the detuning becomes larger, what happens is that now you see that the axis of oscillation, so for example, if you check this one in here, now is no longer the x-axis, but it starts getting tilted, okay? So now we have a circle that is not going from the South Pole to the North Pole, but it doesn't reach the North Pole completely. It's a smaller radius, okay? And then as delta becomes larger and larger, what happens is that the radius of that circle becomes smaller and smaller, but always embedded in the same sphere, the Bloch sphere, okay? And then in particular, when delta becomes very large, the circle becomes so small, okay, that you just remain in the ground state. You will do a very, very tiny circle around the ground state. And that's the limit of delta going to infinity or delta very large, in which we saw that we recover just the free evolution of the atom. And the free evolution of the atom starting from the ground state is to remain in the ground state, okay? So I know that this is a bit difficult to visualize, so then it's very important that we actually show much more friendly observable, which is okay, which is the probability of being in the excited state, okay, the excited state population. So this is now very simple to see, because what we have is this expression here, and what this expression tells you is the following. So here I am plotting the excited state probability, okay, as a function of time, but normalized to omega r. So this is omega r t, okay? Which is the time dependence that appears in the cosine. Then, of course, as a function of omega RT, we always have some kind of periodic behavior because this is a cosine. And in particular, we start from probability 0 because we start in the ground state. So the probability at time 0 of observing the atom in the excited state is 0 because we prepare it in the ground state. And then when the detuning is 0, then this goes up to probability 1 after half a Rabi oscillation, after half a cycle, okay? And then if you continue, it goes down again to the ground state and then back up to the excited state and so on. And what is the effect of a detuning? What is the effect of having a delta different than 0? So I show it here. So the effect of having a delta different than 0 is that now we will get to a maximum, okay, that is no longer exactly unity, but it's a point in here, which is precisely given by this factor 1 plus delta square to the -1. So 1 divided 1 plus delta square, okay? So this is the maximum value that we can get for the population in the excited state. And of course, again, after a half a Rabi period, so half a cycle, but it's no longer perfect state transfer. So we cannot transfer the whole population of the atom from the ground to the excited state. So whenever we put detuning, the effect of the detuning is to reduce the population that we can bring from the ground to the excited state. Only exactly resonant light can bring the atom from the ground to the excited state. Any other light that is non-resonant will always have a probability that is not 100%, okay? So I hope that this is clear. And essentially, this is everything I want to show you about, if I remember properly, yeah, about these Rabi oscillations. And just remember, keep in mind these three limits that are very simple. The limit of very large detuning, in which nothing happens, exactly at resonance, where we have oscillations around the x-axis or precession around the x-axis, and then starting from the ground state for different values of the detuning, we can only transfer partially the population if we are not at resonance, okay? So this is everything I want you to know about essentially the theory of matter without interaction to quantized light. And now I'm open for questions about this part. Otherwise, as usual, you can ask me outside of class anytime. And if you have any question about this chapter, maybe do it now. And if not, we will move to the light matter interaction chapter. Okay, so I don't see any questions. So then let's just change chapters. So actually we don't change very, very much because we will still have our beloved kind of matter system with transitions and so on and interacting with light. But now we are going to make a description of the interaction between light and matter in which everyone is quantized, both the light, the matter, and so on. And in particular, why do we need to consider light matter interaction? So perhaps the best argument I can give you for that is that if we want to prepare states, so the preparation of states, interesting states of light or matter in the laboratory, or interesting dynamics, okay, this will always mean that we need to put in contact our system that might be either the cavity or the atom, and we have to put it in contact with another system that we will use to manipulate it. So in other words, we always need interactions between our atom and our electromagnetic field that we use one to manipulate the other, okay? So then the moment that we have interactions, then we need to have a method to describe these interactions or to make it relatively general. And in particular, here I am going to give you a general idea and then consider a couple of examples. Okay, so the examples that we will study in this chapter are the interaction of light with two types of systems. So this is how I mark the interaction. So first with a single atom, as you can imagine, because from the previous chapter, or also kind of the opposite limit, the interaction of light with a full crystal structure that we call the electric material, in particular a nonlinear dielectric material. Okay, I'm sure you have studied the electrics in optics, and we will review many properties of them in here. But now you are going to understand what is the quantum theory of that system and how you can create quantum states with this kind of materials, just dielectric materials. So these two examples are very specific, but actually they contain all or many of the properties that you will find in other types of interactions. So they are very representative of light matter interactions, and this is why I chose them. And I hope that you will learn basically about these systems, or with these systems, you will learn a lot of examples of how to create states and so on. And before entering into the specifics of these two models, let me give you some general ideas about how do we describe the interaction between light and matter, or the electromagnetic field and matter in quantum physics, and in particular, how we will do it in quantum optics. So let me give you some general ideas. And let me start by kind of giving you the models that you would need to use depending on the energy scales that you are at. So imagine that you are working with frequencies of the electromagnetic field, which are larger or around 10 to the 20 hertz. So these are not optical frequencies. Optical frequencies are 5 orders of magnitude smaller. So these are maybe X-rays and things like this, so very high frequencies. And at this frequency, 10 to the 20, I didn't choose it by chance. I chose it because this frequency is the frequency that corresponds to twice the mass of the electron, okay? So in other words, if you have fields that are so energetic, okay, photons that are so energetic, you can start having production of particles. In particular, you can start producing pairs of particle-antiparticle, in particular of electrons at this energy scale. But if you go to higher energies, then many other particles. And if you are at this scale in which let's say the constituents, the matter constituents of your system can change, so you can start creating electrons out of nowhere, then you need to consider full relativistic quantum electrodynamics, which is the theory that Feynman and other people were awarded the Nobel Prize for. And this, maybe you will study in quantum field theory, because it's the simplest example of an interacting quantum field theory. And in particular, this is a quantum field theory in which the electromagnetic field is a vector field, and the matter fields are Dirac fields. And in particular, the vector field acts as a gauge field that mediates the interactions between the Dirac fields, okay? And if you study quantum field theory, for sure you will see this. But this is a theory that even it's very beautiful, but of course it's much more complicated to calculate things with this theory than with the thing that we are going to use. But of course, we are in a way lucky that our scales are way below this. Okay, and then we don't need to use full relativistic quantum electrodynamics, in particular because in optics, the frequency scales are, let's say, 10 to the 15 tops. And then this allows for non-relativistic quantization, which is, by the way that we have quantized already the electromagnetic field and matter, like the atom. So we haven't done it using the Dirac equation, but the Schrodinger equation, which is non-relativistic. So let me give you a few words about this, because we will not even need to do such a difficult process of non-relativistic quantization. So we will do a non-relativistic quantization, but much more heuristic. Here I want to show you, or I want to just give you the description that you would do if you were to really just take non-relativistic quantum mechanics and just couple the electromagnetic field and the matter degree of freedoms. What you would do is just, you would describe the electromagnetic field with Maxwell equations, okay? But now the matter degree of freedom, okay? So you would not quantize the Maxwell equations in vacuum, in empty space. You will do it in a space in which matter acts as a source of electromagnetic field as well. So you would need to consider the Maxwell equations with sources, okay? And the sources would be the matter degrees of freedom. And on the other hand, to this, you would need to add the evolution or the description of your matter system. And the matter system, it's a multi-particle, or it's described by a multi-particle or many-body Schrodinger equation, okay, in which the coupling to the electromagnetic field is obtained with something that is called minimal coupling. So this is with minimal coupling to the vector potential. So I think that you have studied minimal coupling already, because I know that you have studied quantum mechanics too. And I know that at least in the last semester, you studied the Aharonov-Bohm effect. And for that, you had to couple the electron or one electron to the electromagnetic field, in particular to a magnetic field. And that you did with something that you call minimal coupling, hopefully. Otherwise, that process that you did, it's called minimal coupling, in which you change the momentum of the electron by momentum shifted by the vector potential, because that's the canonical conjugate of the position, okay? But again, I just want to mention this so you have an idea of methods that you would need to use depending on the energy scales and depending on the complexity of your system. So at high energies, you need to apply full quantum field theory in the form of relativistic quantum electrodynamics. In general, in quantum optics, you would need to apply this method of Maxwell equations with matter as sources and the multi-particle Schrodinger equation with minimal coupling to the vector potential. And this would give you a theory of light matter that are coupled, and you need to quantize them together. This is something that in the lecture notes you have references for any of these two methods. So if you are interested in it, you can go and read about it. But here, we are lucky that we can use an even simpler approach, okay, that I like to call, so this is a simpler approach that I like to call, oops, the dipole approximation for the interactions. So let me explain what is this, this method, and I will tell you in a second when does it work well and when it doesn't. So when it doesn't, you have to use one of the other two methods. But this method works very well in certain conditions that we will meet during the course. And it's the following. So just imagine that you have here your material. Okay, your material can be whatever shape. So it's, let's say, a three-dimensional material of some type. And you shine light on it, okay? So we shine some light. So this is light, and this is matter. So let's think about what happens to the lowest level of approximation. So to the lowest level of approximation, just imagine first that the matter that you are examining, imagine that it's just some neutral material, so just any type of material. Maybe it's one atom, maybe it's a collection of atoms, or maybe it's just a, you know, any kind of solid state material. And then to a first approximation, these materials, when you look at one point of the material, it looks like a neutral material, just like an atom is neutral if you don't zoom in into the atom and you see the positive and negative charges and so on. So if you just look it from far away, it's just some energy structure that it's neutral, so it doesn't have charge. But you know, or we know, that actually at every point of the material, what we have are bound positive and negative charges, right? So at the absolutely smallest possible scale, this is because we have atoms, and atoms are bound positive, negative charges. But in many other systems, solid state systems and so on, you will have something similar. So you will have that at the lowest approximation, because the fundamental constituents of matter are positive and negative charges, protons and electrons and so on. Even if the material looks like neutral, you know that deep down there is some kind of positive negative bound state. So then at the lowest level of approximation, what we can think is that when you apply the electromagnetic field, what happens is that these tiny dipoles, okay, that have a positive and a negative charge part, they react to the electric field that is applied that tries to pull them apart. So when you apply an electric field into a dipole, what happens is that the negative charges will want to move in one direction, the positive charges in the other. So then you essentially blow up the dipole, okay? So this theory that essentially, let me summarize it quickly. So this theory in which matter is just treated as a collection of dipoles, of electric dipoles. Okay, and the electromagnetic field essentially acts just by the electric field pulling opposite charges apart. So this is the theory that we call approximations or dipole approximation of light-matter interactions, and it actually works very well. So this theory works very well. Or let me say that it works well whenever you have two conditions. So the first condition is that the interaction can be treated as a perturbation. Okay, So again, this is quite intuitive because what I am saying is that we have a material, it has tiny dipoles inside, and you apply an electric field and the dipoles just, they kind of are pulled apart, but you don't break them. You don't change the properties of the material like completely radically, okay? And in that situation, so when the interaction can be treated as a perturbation, this theory will work. Whenever the interaction is not a perturbation, you cannot use this theory. You have to use any of the other two more complicated theories that I mentioned. And then, of course, the second condition is that matter admits a model in terms of electric dipoles. Okay, let's say that at least under reasonable assumptions. Okay, then when this happens, so when matter admits a model in terms of electric dipoles, this essentially means that we can define a vector field at all points of the material. So at any point r and any time t, we can define, or let me maybe just remove time for now because we will not need it. So you can define what we will call the electric polarization. Electric polarization field, field density, which is nothing but what is the electric dipole of the material so the electric dipole moment of the material, but density, so per unit volume. Okay? So essentially what I'm saying is that the first thing that we need in the description of this kind of light matter interaction is to be able to find out what is the number of dipole or dipole moment per unit volume that we have in the material. So if we have a model for that, then this method can be used. And of course, here I am talking about a continuous material in which at each point you can define a dipole. But of course, this theory works very well, especially when this dipole or this material is actually a collection of dipoles. So imagine that what I tell you is that you have a finite number of dipoles. So imagine that I give you just two dipoles. So one atom that has a bound state of positive and negative charges and another one fixed in space. So this also works. And in particular, in this case, you would define an electric polarization density just by saying something like this. Just by saying that I have n dipoles, okay? And each dipole is fixed at some position in 3 dimensions that it's Rn, okay? So this expression here would be for a finite number of dipoles. Okay, instead of a continuum, I have a finite number of dipoles. This is how you would write the polarization field density. Okay, so if we have these two conditions met, so we know that the interactions are perturbative compared to the Hamiltonian of light and matter, and we have a model for the dipole moment per unit volume in the material, either because we can model it continuously or because we actually have a number of dipoles, then it's very easy to write down what is the Hamiltonian of the full system, light, matter, including their interaction. So under these conditions, you can always say that the Hamiltonian is the sum of 3 pieces. first is the Hamiltonian of light. So this is the light Hamiltonian. Then you will have the matter Hamiltonian. And as I said, this is the main part of the Hamiltonian. This is the part of the Hamiltonian that defines the energy scales and everything. And then you have a perturbation. And this perturbation contains the interaction between light and matter. And what this dipole approximation gives you is actually an approximation for this light-matter interaction Hamiltonian. And in particular, what you can write is that with full generality, the interaction between light and matter is given just by the energy of a dipole in an electric field. This is something that you know from electrodynamics, and it's just E times the dipole. In this case, the dipole density. Because we have a density, we have to integrate over the full volume that the material has, or let's say over the full volume where there is polarization, where there is density, dipole density, and then with a minus. So this is what you have seen in electrodynamics, that is the energy, electromagnetic energy provided by an electric dipole, okay? So this is light-matter interaction within the dipole approximation. So get used to this Hamiltonian, because this is basically the Hamiltonian that we are going to use. So we have the light Hamiltonian that we have already studied in 2 chapters ago, the matter Hamiltonian that we have studied in the previous chapter, and then their interaction given by this. So the only thing that we will need to do is make a model for this polarization density, so electric dipole moment per unit volume, for the specific matter that we are treating. And once we have this, then we simply quantize. So we quantize the degrees of freedom of matter, and we obtain a quantized version of the electric dipole moment, and then we quantize the electromagnetic field, and we obtain a quantized version of the electric field, as we saw already in class, okay? So just a very small remark, because you will hear it all the time in quantum optics, and we might use it all the time as well. So there is something called a semi-classical limit, or a semi-classical approach. To light-matter interaction. And the word semi-classical refers to the fact that the Hamiltonian is the following. So we quantize matter. So we have the Hamiltonian of matter, that it's quantized, but we assume that the field is classical, and therefore we don't have a Hamiltonian for it, but the Hamiltonian is still the same kind of light-matter interaction that I just described, but now the interaction is between a classical electric field and the quantized matter dipole moment per unit volume. So this is the classical field, but matter is quantized. Okay? So whenever you have a theory like this, in which you quantize matter, but you don't quantize the field, that's called a semi-classical model or semi-classical approach. And it's very interesting, and this is why I also want to mention it, that, so you know that all these experiments that are typically explained as the ones that started quantum mechanics, and in particular the quantization of the electromagnetic field and so on. So I'm talking about the photoelectric effect, and I'm talking about the the spectrum of the black body radiation, and so on. So these two examples, in principle, they led to the quantization of the electromagnetic field in packets of h bar omega. But to be honest, that's a description that is actually not required for those systems. The only thing that you require in those systems is that matter is quantized. So the atoms need to be quantized, and let's say the material that is absorbing and re-emitting the light in the black body needs to be quantized. But the field itself, it doesn't need to be quantized, okay? That's something very interesting, because actually that was realized after creating quantum mechanics, and then for many years, the electromagnetic field was not quantized anymore until people started thinking about high energies, and later on in the 60s about quantum optics. But for quantum physics at low energies, essentially, all the theory that was used was semi-classical, in which the fields were just classical objects, and this concept of photons and so on, they were never there. They were not required. And this is really amazing that we started with quantum mechanics quantizing fields, like defining the concept of h bar omega, like quanta of the fields. But then suddenly we realized that we actually don't need it, that all those experiments do not require quantization of the field to be explained, only quantization of matter. So if you are interested about this, you can ask me, because this is a very, very interesting period of time. And therefore, this semi-classical approach is actually very powerful. You only need to quantize the electromagnetic field and do full quantum optics in very specific situations that we will study here, but that in general are not easy to achieve. This is why quantum optics is a relatively young field compared to other things like atomic physics or condensed matter physics, simply because experiments in quantum optics are very hard, okay? So, yeah, so essentially this is what I want to tell you about the general thing of light-matter interaction. So just this light-matter interaction under the dipole approximation. And what we are going to do now is I am going to show you the one specific example, which is the interaction of light with a single atom, okay? This is what we will do for the rest of the lecture today. And then in the next lecture, we will also study another example, which are the interaction of light with a big material. So a material with many, many, many atoms called the electric material. Okay, so let's study then the interaction of light with a single atom within this dipole approximation. So of course, we are going to study the type of atoms that we have already introduced, in which we have a single balanced electron. Okay, and in particular, I remind you that essentially what we said is that we have kind of a positive cloud in the center that is very massive. And then we have our valence electron that has negative sign. And then we have an interaction between this valence electron and the positive core. So we will call the relative distance between them, we will call them R atomic, okay? Just to distinguish it from the previous R, that it's actually the position in the three-dimensional space, the position in the material, okay? So one thing is the position in the material, and a different thing is the relative distance between the positive and negative charge that we call R atomic, okay? So for this material that is a single atom, the normal R would correspond to the center of mass of the atom, okay? So this is what in the previous chapter we were just calling R, but here we call it RA to make this distinction. And then, of course, why do we study this case initially? Because actually this, so a single valence electron is the perfect example of a single dipole. So we have a positive core, we have a negative thing around it. So that's exactly the definition of the classical definition of a dipole. And in particular, the dipole moment of this structure will be minus E and then proportional to the distance R. Okay, this is what you see in electrodynamics, that the dipole moment of this positive negative structure is just essentially proportional to the distance between the positive and the negative charge. Here we are assuming that both of these charges have charge 1, okay, +1 and -1. And the minus sign simply comes because usually the dipole moment is defined from negative to positive, okay? But in our case, or in the case of the atom, we define the relative coordinate between the proton and the electron from positive to negative, as I have shown in the picture, so in this figure, okay? So now, because we have the simplest example of a single dipole, or the simplest example of matter that it's actually a dipole, we can use the previous Hamiltonian. And in particular, what we are going to do is we are going to put the atom inside an optical cavity. Okay, and we put it at some position, for example, so the center of mass of the atom at position R0, that it's simply at some position in the cavity. Remember that we were doing a one-dimensional approximation for the cavity, and then the optical axis, so the axis of the cavity is the axis Z. So we just assume that the atom is sitting at the center of the XY plane at some position in the cavity Z0. And then the interaction between light and matter in this case, so it's just given by the product of the quantized electric field, inside the cavity, times the dipole moment, which is E times R. And of course, R is quantized as well. So I hope this is clear. But of course, this comes from the fact that we have a single dipole, and therefore this polarization that we define, P of R, this is just the dipole moment D times the delta function at the position of the atom. Okay, so if you just take this definition of the dipole moment density or polarization density, and you put it in this expression, you get exactly this this Hamiltonian. And this is the Hamiltonian that we will use. So you see that it's very simple. It's just a multiplication of the electric field times the relative coordinate of the atom. And just one remark, I think it's clear, but we have made an implicit assumption. And the implicit assumption is that the electric field E is constant over atomic scales. Okay, this, I call it an assumption, but it's actually a perfect approximation. Like, just think for a second, what are atomic scales? Atomic scales are something like 100 picometers, okay? That's the typical, let's say, size of an atom, like distance between the electron and the proton. And what are the typical variations or the scales over which you can observe a variation of an optical field? This is the wavelength, and the wavelength of the field is always around hundreds of nanometers. So of course you see that the atom is much, much smaller than the variation or scale of light, okay? So this is light's wavelength. Okay, and these are atomic scales. And therefore, we see that essentially within the space of the atom, okay, the electric field is essentially constant. So it's just given by the electric field at the center of mass of the atom, okay? This is why we can simply write such a simple expression, just saying electric field at the position of the atom, okay? So essentially we have now a model that describes the interaction between light and a single atom that is located inside an optical cavity. And this model is just the product between the electric field inside the cavity and the relative coordinate of the atom, which comes from the fact that the dipole or the atom can be seen as a dipole that is proportional to the distance between the positive and negative parts. Okay, so what we are going to do now is we are going to essentially simplify this Hamiltonian, or just work out this Hamiltonian, and then solve for the eigenstates of the Hamiltonian and all these things to see which kind of physics appear compared to the situation in which we don't have any coupling between light and matter. So let me go ahead and let me tell you what we are going to use. So of course, the things that we are going to use are the following. So to start writing the Hamiltonian, this is no approximation. It's just using expressions that we have already seen. So first of all, the electric field, E of z, we have already quantized it in chapter 2. And we saw that the expression for the quantized electric field, it's something like this. So it has a polarization that we chose along the x direction, just arbitrarily. And then we have the modes of the cavity that are described by an index or labeled by an index m. And then we have this kind of normalization factor, h bar omega m divided epsilon 0 L S, and then the mode function, so the spatial profile of the mode function, which in this case is just a standing wave inside the cavity. And then we have the annihilation and creation operators associated to the modes inside the cavity. So this is the quantized electric field inside the cavity. And on the other hand, we have seen in the previous chapter the quantized form of the atomic coordinate. So in particular, if I call, like we have done already in the previous chapter, but just to make sure that everyone remembers, the atomic basis of energy eigenstates, we were denoting them by these quantum numbers n, okay? And then I can use that as a basis in the space of the atomic system. In particular, I can represent the coordinate, this r, I can represent it in that basis. So I can choose the basis n prime, and I will have here the matrix elements of this operator, and then the outer product of n prime. Okay, so this is just a representation. Sorry, this is RA. And the only important thing as well, I mean, it's not super important, but just you remember that this matrix element here, and this is why we talked about this in the previous chapter, this matrix element here, I remind you that it's non-zero only when the parity of the atomic eigenstates is different. Okay, we already saw this last week. So this means that this sum actually doesn't run over all the possible states, but only on states that actually have opposite parity. So initially, let's say that this is the general form that we can write, the most general form that we can write for the operators involved in the Hamiltonian. But we already know much more. So we already know that, imagine, okay, that we have a situation in which only, maybe, let me represent it here. So imagine that we have the situation. So this is the approximation, let's say, but it's not an approximation in the sense that this can be done like that in the lab. It's not a physical approximation. Imagine that only one particular mode, omega m, okay, so m mode, cavity mode, is close to resonance to only one transition. So one specific transition. So one En prime, okay? So the situation I am describing is essentially the situation in which we have the cavity and we have the atom inside. The cavity has many modes, but actually only one of these modes, okay, only one of these modes that has some frequency omega is actually resonant with the transition between a ground and an excited state of the atom at some frequency epsilon, okay? So what I am saying is that there is only a single omega that is more or less equal to epsilon, okay? So then in this situation, just like we have seen in the previous chapter, we expect that we are able of doing what we will call as well the two-level approximation, okay? In which now out of all the atomic states, we only care about two. So we care about one ground state and one excited state. And therefore, this whole structure here can be written, or this whole operator Ra can be written in this way with the matrix element G, R, A, E, okay? And here I have assumed for simplicity, okay? This is just for simplicity, that we have a situation in which this matrix element is just real, okay? So in general, this matrix element is complex. So this will be, this will have something in the complex conjugate, okay? So it will not be proportional to sigma x, which is this part in here. It will be a linear combination of sigma x and sigma y, okay? Because this element here will not be real, it will be complex. But that just complicates a little bit more the math, but it doesn't have any physical effect. And actually you can redefine, let's say, coordinates and axes and so on to remove that complex dependence. So, so essentially, this is an approximation or an assumption just for simplicity. Then on the other hand, we can do a single mode approximation in here in the electric field. Single mode approximation. And what is the single mode approximation? That out of all the modes that are inside the cavity, because there is only one that will fill the atom, we only care about that mode. We call it with frequency omega, so we remove the label n, and therefore the electric field can be written in terms of that mode just in this way. H bar omega divided epsilon 0 ls, the mode function, and then A minus A dagger. Okay, so I will just call A and A dagger the annihilation and creation operators of that specific mode that is close to resonance with the atomic transition. Okay? So essentially, this is the situation that we are going to analyze. And it's a situation that typically happens in a lab. So in a lab, you have atoms, you put the atoms inside of some kind of cavity where you have quantized light, and then you make sure that only one transition is resonant with one cavity mode, so that you can manipulate easily both the light and the atom. So then in these conditions, the Hamiltonian looks or takes a much simpler form. So the final Hamiltonian, including the Hamiltonian of light and the Hamiltonian of matter, is just given by h bar omega a dagger a. So that's the Hamiltonian of light. Then h bar epsilon divided by 2 sigma set. That's the Hamiltonian of the atom, as we have seen it in the previous chapter. And then we have the interaction, and the interaction can be written just as I h bar j. So the I comes from this I factor in here in the electric field, okay? And then we have the multiplication of the electric field, which is A minus A dagger, times the coordinate, the atomic coordinate, which is sigma x. Okay? So this is the Hamiltonian that describes the interaction of a single mode of light with a single atomic transition. And this is known as the quantum Rabi Hamiltonian. Okay? And in particular, in this quantum Rabi Hamiltonian, if you just substitute everything in the previous form of the general form of the Hamiltonian, you will see that this coefficient or interaction coefficient G is just written in terms of the physical parameters of the model as the charge of the electron, the frequency of light, divided h bar epsilon L S, then the matrix element of the atomic coordinate, but projected onto the polarization of light. And finally, the mode profile, so the standing wave associated to that mode at the position of the atom set 0. Okay? But this parameter is not very important. I mean, the form of the parameter is not important. The only important thing is that everything about the interaction between light and matter is contained in a single interaction parameter that we can call G, okay? And perhaps just something important to remember if you work in quantum optics is how can you control the strength of this parameter, okay? Or how can you control which transitions are you coupling to? And this is very nice because apart from the frequency, okay, apart from the frequency of the light field that has to be resonant with the transition, you have one more condition that it's kind of here, okay? That you see that the matrix element that matters is not just any matrix element or any direction of the coordinate vector, but is the one in the direction of the polarization of light. Then by choosing different polarizations, this matrix element takes different values, and you can make it such that you excite only specific transitions in the atom that, for example, have an exchange of angular momentum +1 or things like this, okay? And so all these things are used all the time in the lab, like playing with polarization and with frequencies such that you excite specific transitions that you are interested in the atom. But mathematically, the only important thing is that we have a Hamiltonian that has a harmonic oscillator term for one electromagnetic mode, a two-level system free term for the atomic transition, and then some interaction between them that goes through one quadrature of the electromagnetic field, in this case, the P quadrature, A minus A dagger times sigma X, okay? And then this is the Hamiltonian that we need to solve. So it's really interesting that this Hamiltonian, even if it looks so simple, it remained actually without analytic solution. Okay, so it didn't have an analytic solution until recently, so maybe 10 years ago or something like that. Even though this Hamiltonian has been used all the time, but no one managed to find an analytical solution to it until very recently. But even the analytical solution of this Hamiltonian that we know nowadays, it's actually very complicated to use. So in practical terms, we have it. It's a mathematical expression that is very complicated and so on, but it's very difficult to actually use, okay? So then people have found ways of solving this Hamiltonian under certain approximations. And we can make actually one approximation that we have already used for the atomic case, which is a rotating wave approximation. And this is what I will show you exactly now. So we can make one further approximation that will make the problem easily analytically solvable. And this further approximation it's simply the following, that if the interaction G is much smaller than the frequencies involved in the process, so the atomic frequency and the optical frequency, and this is something that happens, as I said, very, very naturally in optics. So maybe you can give it a try about calculating this for one specific transition of one atom and so on. You have it in the quantum optics books that I recommend in the lecture notes and so on. And you can see that this thing here is always very small, okay? It's very small. Let's say on the order of kilohertz, megahertz, and things like this. Maximum is very difficult to go beyond that. And as we said, optical frequencies are really 10 to the 15. So then this is something that we call it an approximation, but it's actually very, very well satisfied in optics. And then in these conditions, we can do what we have called the rotating wave approximation. Okay? So in order to see the rotating wave approximation in this problem, the best is to change to a new picture. So we are, let's say, imagine that we are in the Schrodinger picture, and I want to describe the physics in a different picture. So then let me make a small detour. Okay, so let me do a detour in here, because I think I still didn't explain how to change pictures. So let me explain you something very basic in quantum physics. So this is for all subjects that have quantum physics. How do we change to new pictures? So we have seen the Schrodinger picture, we have seen the Heisenberg picture, but what I want to show you here is that we can actually work in many other kinds of pictures or intermediate pictures that are not full time evolution only of states or full time evolution only on operators, but something intermediate. And I will, so in the lecture notes, you have it already, but I will write it in the part in the introductory chapter about quantum mechanics, because I didn't put it there, I put it only in the appendix, but I will write this thing that I am going to explain in there. Here I will explain it only from the Schrodinger picture, but there I will do it also in the Heisenberg picture. So imagine that we are in the Schrodinger picture. So from the Schrodinger picture, which means that in this picture, operators do not evolve in time, but the state evolves in time, according to an equation that we have already seen, that is the von Neumann equation. Okay? Or equivalently, just the unitary, so the evolution generated by the time evolution operator. Okay? So now I know that you know how to change pictures, but this is something that is very used in quantum optics, and I will give it one specific form that we like very much in this field, which is, it goes as follows. So what does it mean to change a picture? Or how does it come? It comes from the following thing that we already saw in the equivalence between the Schrodinger and the Heisenberg pictures, that in quantum optics or in quantum mechanics, we only care about expectation values of operators. We only care about statistics of experiments. And this means that we only care about objects such as this one. So the expectation value of an operator A, okay, at any given time t, which in the Schrodinger picture is given by this expression, the trace of the density operator at the time t times the operator A. But of course, because of the cyclic property of the trace, I can always do the following. I can add here an identity in the form of a unitary transformation. So let me make sure I use the convention I want to use. Okay, and I do the same in here. So I put here another identity. So I define, or I take a unitary U, UC, U sub C, that it's any unitary I like, whatever, even time dependent, like any unitary that I like. If I put the unitary there, I am doing nothing because this is the identity, U dagger is just the identity. But using the cyclic property of the trace, I can bring this U in here, I can bring it to the other side, and then I get this expression here that it's very suggestive. So I have U dagger C that might depend on time. So we will make it time dependent, acting on the state. And then we have the same acting on the operator. Okay. As I said, this U is an arbitrary unitary. So whatever you want. But then I can see this and this as a new state that I will call rho with a tilde. Okay. And this is a new operator that depends on time. Okay. That defines a new picture, a new way of looking at how the state evolves. So in particular, talking about the state is given by this transformation U dagger C of t U, but now I have to write rho of t, but rho of t is nothing but U of t acting on rho of 0, and then U of t dagger, and then in here I get UC of t. And now you can understand why I chose this form of the unitary. I putting the dagger on the left and the non-dagger on the right, because now see, the interpretation of this, of rho tilde, it's very clear. What I am doing is, so we have the state that is evolved through some natural unitary. So let's say is the unitary that comes from the Hamiltonian of the system, okay? And therefore, what we are doing here is just discounting, because we are applying U dagger. U dagger is the inverse of U. So we are removing part of this evolution, okay? So we have rho, so we have the state that it's evolved by a unitary U, but then we decide to remove part of that unitary with another unitary that we define, okay? And I will show you one specific example now, very generic example. So what I am saying is that what we are doing is essentially discount, okay, the evolution UC of t from the full evolved state rho of t, okay? But of course, if we remove it from the state, we add it to the operator, okay? And this is also very simple to see because now the operator is no longer not a time-independent operator, but it's a time-dependent operator that depends on this unitary that we are discounting from the state. However, if this unitary is something that we know, this operator is something that we know. I mean, we don't need to solve the dynamics of this operator. We already know it. And in particular, this means that in this new description of the state of the system and the observables and so on, observables evolve according to this trivial evolution. Oh, sorry, I didn't want to write that. So I wanted to do something slightly different. Let me see, yes. So I'll give you first the evolution of the states. So the states, in this new picture, you can show very easily just taking the derivative of this expression here, okay? You can show very easily that the new state, or the definition of the state rho tilde, it evolves still according to a von Neumann equation, in which we have a new Hamiltonian that we will call HI. The I comes from a tradition of calling this interaction picture, okay? So this is the evolution equation satisfied by the state in this new picture, in which we have transformed everything with a Hamiltonian, with a unitary that we chose. And this Hamiltonian, this interaction Hamiltonian, it's just a very simple one. It's the original Hamiltonian H, but we transform it with the unitary. So we have UC dagger UC. So of course, because UC depends on time, the Hamiltonian becomes time dependent even if it wasn't time dependent. And we have a part that comes from the time dependence of U, which is this one here. This is the derivative of U dagger times U. Okay, let me make it a bit more explicit. So the dot on top of the unitary, so this thing here, okay, that means time derivative, okay? So this is a very simple expression that you can show that the new state evolves according to a Hamiltonian that is the original one transformed by the unitary, and you subtract this funny expression, U dagger derivative in time times U. So this is UC, sorry. Okay. And what's interesting, or something that is very important, is that when as a unitary, if as unitary, we take something that has the form of just a time-independent Hamiltonian, okay? So imagine that you don't choose just any unitary, but you choose a unitary in which you want to discount the evolution associated to a time-independent Hamiltonian HC. Then all this thing is just HC, okay? So then the final Hamiltonian is just the original Hamiltonian transformed, and then you subtract the Hamiltonian HC that defines your transformation. So in this situation, actually, so if this is the case, then the evolution of the states is given by this equation. Oops. Sorry, of the observables is given by this equation, which looks like the Heisenberg equation, but it has as a Hamiltonian just the transformation Hamiltonian. So the Hamiltonian that you are using for doing the change of picture. So HC. Okay? So long story short, we can always define a new picture in which our state evolves according not to the original Hamiltonian, but the transformed Hamiltonian minus some Hamiltonian that we want to remove, okay? So some evolution that we want to remove. And in that case, the states, sorry, the operators will also evolve in time. So this is something that I usually like to call intermediate picture. Okay, because both, so where both states and operators evolve. Okay. However, as I have explained, in this case, operators evolve trivially. So you have to take into account that they evolve, but you know how they evolve because the Hamiltonian has been chosen by you. So these kind of changes of pictures are very, very useful in quantum mechanics, both to see approximations like we will do now, or also just to solve problems analytically or numerically. So this is something that you need to understand perfectly, like how to change pictures in quantum mechanics. This goes beyond quantum optics. But this particular form is something that we will use a lot during the course, okay? This kind of change of picture. So let's apply this change of picture to the previous Hamiltonian that we were analyzing. And in particular, let's change to something that we usually call the interaction picture. So change to what we call the interaction picture. And what is the interaction picture? The interaction picture is just discounting the evolution given by the non-interacting part of the Hamiltonian. So this means that we do a transformation with a unitary described by this HC, that it's just the Hamiltonian of light plus the Hamiltonian of matter, okay? So if you take that, you take the non-interacting part and then you make the change of picture. So first of all, it's very important that you know what is the action of this UC onto the basic operators of your system. And in particular, because H of light is just A dagger A, okay? So I remind you that this is HL, this is HM. We know the commutation relations of A dagger A with A and the commutation relations of sigma Z with sigma X and sigma Y and sigma and so on. Then it's very easy to actually find how this unitary acts on A. And I think we already actually saw in chapter 2, or at least implicitly, that this is just given by this expression here. So if you apply the unitary evolution associated to the Hamiltonian of light, this just gives you e to the minus I omega t, okay? And if you do the same now onto the lowering operator of the atomic excitations, then this gives you actually the same, but now with the atomic frequency. Okay? So you can check this. It's very simple to check it just with the Baker, Campbell, Hausdorff lemma that we have used many times already. And then using this, now we can write the Hamiltonian in this interaction picture. And the Hamiltonian in this interaction picture it's very interesting. It looks like this. So it has two parts that are very well defined, and let me just write them down first, and then we discuss them. So we have this. Sorry. And we have this, and then we have another piece in here that has a similar expression, but now looks like this. Okay. And now this is a very nice Hamiltonian because it allows us to see the time scales of the problem. So in particular, you see that why we call it interaction picture, because we have removed from the Hamiltonian everything that is not interaction. So all the parts that are just acting on the Hilbert space of the atom or light alone, that's away. And here we have only the interacting part, the term that has A's and sigmas, okay? On the other hand, you see that this part in here, so this term in here, that we will call HR, this term oscillates slowly. Why does it oscillate slowly? Sorry. Or at least we expect it to oscillate slowly because we expect that omega needs to be close to epsilon. This is the assumption that we made at the beginning, that we are close to resonance. And therefore, omega minus epsilon is something small. Small compared with what? Small compared with the oscillations of this term in here, that we will call H and R. You will understand in a second why we call them R and R. Because, so this one oscillates fast. And it oscillates fast because it's just the sum of omega plus epsilon in the oscillation, okay? And therefore, we have already seen that whenever we have a part that oscillates quickly and a part that oscillates slowly, we can neglect the fast oscillations. That's what we call the rotating wave approximation. So we can do a rotating wave approximation, and essentially this means that this term in here is negligible within the rotating wave approximation, okay? So what we will do is that we will keep only this part of the Hamiltonian, and this part it's easy to diagonalize, as I will show. But so apart from these slow and fast time scales of oscillation, I want to discuss one more detail that it's also very interesting about this kind of Hamiltonians, which refers to energy conservation. So as I was saying, we are going to the interaction picture, meaning that we have a clear interacting part and then a part that is non-interacting. And in particular, in general, we can say that the Hamiltonian might have two parts. One defines the energy scale, or one sets the energy scales. Okay, so in our case, this is so because the interacting part is just a perturbation. So this means that the energy scales of the problem are already set by this non-interacting part. And therefore, now we can analyze whether the processes that are induced in by these interactions conserve these energies or not. And you can see that this one it's energy scale conserving. Because when you absorb a photon, you excite the atom. Or when you de-excite the atom, you emit a photon. Okay, so this means that every time you perform a transition in the atom, this goes accompanied with the process of emitting or absorbing a photon. And this preserves the energy. The energy in the sense of this scale set by the free Hamiltonians. On the other hand, this one in here, it's actually non. So this is energy scale non-preserving. Because this has very weird terms. Look at what happens in here. You are creating at the same time a photon in the field and an excitation in the atom. But this is a process that is very weird, no? Because you are exciting the atom without absorbing a photon. You emit a photon at the same time, okay? So these processes are very, very suppressed by energy conservation, okay? And could only happen if actually the energies are not defined by these scales. So whenever G is very large and then the interaction is not a perturbation and you cannot claim that the energies are approximately the ones given by this part of the Hamiltonian, then you cannot do this argument because this is not energy anymore. It's not absorbing a photon doesn't mean that you are conserving energy or not. But in this situation in which HC really sets the energy scale, then this term in here can also be neglected because of energy conservation, okay? So this is all I wanted to say today. We will continue from here, and in particular, we will solve analytically this Hamiltonian, that it's very simple to solve, and we will start finally seeing physical effects of light-matter interaction, but this will come next week, okay? So I hope that you like the class of today. It was much more conceptual than actually physical or mathematical, and the next one will be kind of the opposite, a bit more mixing more math, but also a lot of physics. Yeah. So thank you for listening, and see you next week.